Om Shri Sai Ram. Respected teachers, colleagues, and my dear brothers and sisters, it is my great privilege to introduce to you our next speaker, Dr. Jyotishman Dasgupta, Associate Professor, Tata Institute of Fundamental Research, Mumbai. His academic journey began with an integrated MSc program at IIT Kharagpur, PhD at Princeton, postdoc at University of California, Berkeley. Then he went on to join Department of Chemical Sciences, Tata Institute of Fundamental Research, Mumbai, as assistant professor. Currently, he is an associate professor there. His research interests include designing new materials for photo-induced charge generation, developing new photoreaction methodologies, time-resolved optical spectroscopy of pi-Conjugated materials. He has published a total of 108 papers, with some prominent publications being in journals like Nature, Science, PNAS, JACS, JPC, etc., with a total of 642 citations and a H index of 20. He is also a recipient of a number of awards. Some of the prominent ones are: he was chosen as the best emerging young investigator in chemistry of materials meeting India, held in the year 2018. He was also awarded the 2017 Young Scientist Award for the Asian and Oceania Photochemical Association. He happens to be one of the founding members of the Fluorescence Society of India. He is also in the editorial board of Nature Scientific Reports. Today he will be speaking to us on the topic watching excitons in pi-conjugated organic materials using time-resolved optical techniques. Over to you, Jyotishman.
Hey, well, thank you, Dr. Kiran, for this very nice opportunity. And of course, thank you, Professor Ravi Kishore, who was kind enough to invite me to this event. And that, the Sri Satya Sai Institute of Higher Learning is organizing this particular event termed as Recent Advances in Chemical Sciences. I think I was sort of very interested in listening to some of the yesterday's talks, and today also Dr. Rachna spoke about process analytic technologies, which were very relevant to what the contemporary technologies are about for imparting the knowledge from research labs to industries. So I think I guess the organizers have done a fantastic job of getting both researchers from the fundamental sciences to actual scientists doing the work in industries and developing technologies. So thank you for bringing me to this forum. So today I am actually going to talk about photovoltaics, organic photovoltaics, actually solar cells as we call it in simple terms. And for those students who are with me, listening to me right now, I just wanted to tell you that this talk would be sort of a guide to what the current contemporary research is in the area of organic solar cells. Of course, there are multiple areas of research, fundamental research in photovoltaic technologies and photovoltaic science. But this talk that I have prepared for all of you is really going to focus on how to think about the idea of light harvesting, light trapping, from the perspective of materials that a chemist really loves to make. So here the talk title is has been shortened today. I just made it a little bit shorter than what I had given originally, but it has the same content and the same feel. I've titled it as Watching Excitons in Pi-Conjugated Organic Materials. Okay. So the word excitons is of course new to many of you who are hearing it for the first time. And as the talk progresses, I'm going to define it better and better. However, just to start off, what excitons really mean? When light actually gets absorbed by organic materials or any kind of material, um, inorganic as well, you create excited electron hole pairs. Okay. Now these excited electron hole pairs are termed as excitons. Okay. So if you were to follow my pen here, um, so here. Yeah, the pen here. This is the word exciton, which is an electron hole pair. So what I would delve into today is shown in this particular cartoon representation, that when I create light absorption event in polymeric materials, which are really the heart of organic solar cells, these polymeric materials absorb light and they create these electron hole pairs, these positive and negative charges together. And these excitons, they behave as particles. They're essentially pairs. They move together and they can diffuse in the organic part and come to an interface with another different kind of a material, which is its redox partner, and then there would be an electron transfer. That means the electron and the hole separate out. Now they are not traditional excitons that were generated by light excitation, but they become anions and cations, radical anions and radical cations on a molecular framework. So these are charges, so as to speak. And once you can separate these charges out, okay, in opposite directions through an electrode, you can generate electricity. Okay, so that's the idea. You generate charges and then you separate across two different electrodes and you can make a working solar cell. The second image that I have kept here is essentially our own viewpoint of how excitons dissociate in an organic pi-conjugated material, in a solar cell material. And this is something that will be the main topic of our discussion today, where I will enumerate how, as a chemist, you can make these kinds of materials where you have a donor, electron donor, and an electron acceptor connected through a bridge moiety. And these are all molecular entities. That means the bridge could be any kind of a pi conjugated chromophore. It could be thiophene in this case. This is thiophene. This is the sulfur containing heterocycle. And you can choose any kind of donor and acceptor. But what the viewpoint that I will try to bring here in this talk is, at the molecular level, these excitations have a molecular basis. They actually are strongly connected to motions in the molecule. And when these excitons or excitations diffuse, they actually lead to nuclear changes or structural changes in the molecule. Okay, so in order to capture the essence of a moving exciton, you really need to watch the molecular framework, the structure of the molecular framework evolve. And that's what we try to do in our lab. Okay, but let's give context to this very specific question. Why do we actually need to watch excitations? Why do we need to watch molecules evolving as excitations are moving from one part of the solar cell to another interface within the solar cell? Why is it so important? Well, the bigger context is the energy status in the country. Okay, this is something that I keep as a starting point, as a slide, to sort of discuss that we are really facing an energy crisis, because almost 4 to 5 years back now, you can clearly see that we still have so many 10,000 or 20,000 villages and 50 million households without power. Okay, and when we look at this data from 10 years back, we had almost 160 gigawatt of energy production. The electrical energy needs in almost 10 years from now would be 5 times that current production. And that is a huge ask, okay, for a country that is developing. The population is continuously increasing, our lifestyles are improving, and that's all for the better. But we are asking too much from our own technologies, and we have to satisfy our electrical energy needs. Of course, the commercial energy like gasoline and petrol is also going to be increasing almost 3 times from the current needs. Okay, so it becomes imperative to think of solutions, technological solutions to the energy problem, which sort of may be easier to get. And of course, the government rightly has a target that it wants to go solar. Okay, and solar energy becomes an important um, part of this entire big puzzle of how to satisfy the energy needs. And one of the goals is by 2022, which is the next year, we should have 100 gigawatts of solar power in India. Okay. Now, currently, to this year ending 2020, the ministry had released information that almost 37 gigawatts of solar power is now being installed in India. It still is a big ask to get 70 more gigawatts. Okay, all of these solar technologies are silicon dependent. Okay, and it becomes important to get away from silicon because the cost of silicon and the manufacturing cost is huge, and China holds the sort of proprietary part of creating crystalline silicon wafers. So this becomes important that as a country, as a nation, we try to at least figure out technologies that would be inexpensive as compared to manufacturing of silicon solar cells. So, of course, world over, that's the quest. But just to look at some numbers, why do silicon solar cells win? It's simple because the efficiency of silicon solar cells are close to 29 to 30%. This is a chart that National Renewable Energies Lab, which is in the US, NREL, they release every year. And you can clearly see that there are different technologies that are available, that are growing to reach that 29 to 30% mark. Okay, something that you would see at the top of this table. This is part of the entire map. I did not show the entirety, but you can clearly see, if you can read this, this is 29%. And there are other technologies like emerging PV, okay, that are sort of raising the efficiencies of these solar cells, which are called third generation solar cells, to reach the silicon benchmark. This was very nicely shown by Gary Hortz from the Weizmann Institute in 2014 in a review paper in Science, how other technologies are catching up with silicon. These numbers, of course, have changed. Perovskites, organic photovoltaics, OPV, dye-sensitized solar cells, and amorphous silicon, not crystalline silicon, are in the race to capture that coveted spot for what crystalline silicon does. So you can see that perovskite solar cells and organic photovoltaics have a big jump in the last 20 years or 10 years, right? And they're going up. And that's really the sets up the question for what are the materials that you can use to make a solar cell. They need to be cheap, of course, and what is being understood is they could be molecular in nature. That means a chemist can participate in developing a new technology. And as you know, silicon is silicon. Silicon is never going to be changed. Okay, you can dope silicon, but silicon's characteristic cannot be changed. Its element cannot be changed. But with organic molecules, you can synthesize a plethora of different kinds of molecules, which is in your hand, which is in your control. And as a chemist, you take pride to make molecules. So that becomes the source of imagination for all the scientists in the solar cell community with the third generation solar cells, molecular sources, that means organic photovoltaics. And that really drives this question, this part of the question, and drives us as well as part of the community, because we believe that actually there could be a molecular solution, there could be an organic solution to this problem. And it really comes out from the chemist's perspective of making new materials. But of course, not just the pure material that is interesting, but how to interface these materials with electrodes, how to make devices with these materials, how to process this material. That also requires technology. And as you heard from the previous speaker, Dr. Rachna, that there is a huge lot of investment in process analytics. And you really, once you come up with this material, you really have to have a process analytics for this kind of a solar cell as well. And of course, apart from looking at materials and interfaces and making a solar cell, you keep trying to push the efficiency higher and higher by keeping the base material same, but thinking of ways to include new physical insights and new physical mechanisms of light trapping. Something that I might enumerate at the end of this talk if I have the time. The things like multiple exciton generation. That means a single excitation with one photon, of course, typically generates one electron hole pair as together, right? However, there are processes, there are materials in which you can have two such excitons generated per photon, which just increases the light trapping efficiency of a material. Okay, so there are varieties of different places that you can invest time in, with respect to the molecules and with respect to the materials that a chemist makes. You can make small molecules, you can make dye-sensitized solar cells with small molecules. You can make organic photovoltaics with conjugated polymers. You can again use quantum dots, which are inorganic materials, small inorganic nanomaterials of 5 to 10 nanometer sizes to make a solar cell, because they can trap light and they're all tunable. And of course, you can make this new kind of material. It's an inorganic system, which is a perovskite system, inorganic organic perovskite systems, which are films of material, crystalline material, which can also be used. And it's fantastic now. It's catching up like as a new wonder material for making solar cells. Okay, so I'll go through some of these aspects. However, I will not touch upon small molecules or quantum dots or even perovskites. Even perovskites are one of the most exciting prospects, but I will really work with, and I will really talk about conjugated polymers, simply because conjugated polymers are organic materials. They have covalent bonds in them. They're strong bonds, and they have a very good chance to be robust. Perovskites, however, are self-assembled, and they can, fall apart after some time. They could get damaged. And perovskite solar cells do not survive for a few days, for more than a few days. So as a technology, we would like to compete with silicon, which lives for 30 years as a solar panel. Perovskites will not live for more than few days at this point. There are ways now to make them stabler, but it is not in years yet. Conjugated polymers have been successfully being translated into technologies, and they're showing promise to be robust in years. Okay, so let's first analyze the entire situation. How do these materials really differ from silicon? So in silicon, we know that any kind of excitation in silicon leads to a direct generation of free carriers, free charge carriers. That means the holes and the electrons, of course, they are paired up, but they are free because they actually have a large exciton radius. Okay, so the excitonic radius in silicon, that means the pairs come about forming a distance of close to 10 to 20 nanometers. They're separated by that much of a distance. And because the Coulombic interactions are weak because of the high dielectric constant of silicon, these interactions are weak. The binding energy, the Coulombic binding energy, is 10 milli electron volts, which is half of room temperature, the thermal energy at room temperature. That means it is half of 0.5 kcals per mole. You know this CC bond rotation in a ethane, right? It's around 0.6 kcals per mole. The binding energy of an electron and hole pair is close to half that energy. That means at room temperature, which is close to 0.5 kcals per mole, they can easily be free. They don't see each other. They don't feel like they're paired up. Okay, they're weakly interacting, and they can become they can be moved out of the conduction band and the valence band very easily by using an electrode. Okay, so in silicon, the excitations are called one-year excitations or excitons. they are weak in character interaction, and hence they're easy to generate. It's easy to generate free charges from silicon and make a solar cell. However, in conjugated polymers like this, you sort of can tune band gap. Silicon, you can't tune the band gap. However, in conjugated polymers, you can change the band gap. That means the valence and the conduction band energy separation. You can change it. However, and you can generate different colors. However, it becomes hard to conceptualize excitations, electron hole pair, just like in silicon. Okay, in conjugated polymers, these excitations are strongly bound. They're strongly connected to the framework. The framework is the organic framework. That means the electron excited from our donor system to an acceptor system. For example, if you can watch my cursor here, they are pretty strongly interacting with the molecular framework. You can't take an electron out because each electron is bound tightly to the nuclear part of the molecule. Okay, so this is this problem of charge generation in organic materials. Okay, the problem is the exciton binding energy. That means once you generate the excitation, that electron and hole, they don't really separate out. They actually are close to less than 1 nanometer. That means the electron and hole are really lying close to each other, and they are strongly interacting. You can see the binding energy of the electron and hole is 7 to 21 kilocalories per mole. It's a large energy. Okay, room temperature is 0.5 kilocalories per mole. So you can see clearly it's an order of magnitude larger than room temperature. So at room temperature, thermally, you cannot dissociate the electrons and holes and create free carriers. That's a problem. But chemists know how to overcome this problem, and they create these interfaces, molecular interfaces of two different kinds of redox activity. Okay, that means one can be an electron donor, the other could be an electron acceptor. So the energetics of the system, where the HOMO and the LUMO is for this molecular system, you can adjust, you can choose such energetics that you once excited one of these molecules with large excitonic binding energies. If this donor is excited, the red sphere here, excited, if it is close to an acceptor, the electron can hop over to the acceptor and break this stronghold of Coulombic interaction. Okay, so once this goes away, the electron moves over, it loses the memory of the original backbone from it was created, right? And now the electron is freer as compared to what it was originally. The 7 kcals per mole really drops down to 1/10 the energy because it's still coulombically bound, because the molecules are still close by. It's still an interface, and still Coulombic interactions will take place, but these will be 1/10, close to the silicon energies. Okay, so these are the common molecules that are used. Polythiophene is the most commonly used material for making organic solar cells. And fullerene, that means these C60 structures, which you have seen, or C71 in this case, structures, or C60 or C71 structures, those are actually one of the most popular ways to create organic solar cells, these interfaces, donor and acceptor interfaces. And with that, because of the charge transfer step, you can make weaker exciton binding energies, and then using your own chemistry tricks, where you can assemble things together in one phase versus another phase, you can start moving the holes and electrons in opposite direction, so that you can attach an electrode and generate, light up a light bulb, right, for a solar cell. You can also, of course, do catalysis, which chemists love to do, by separating charges. That's not what I'm going to talk about it today, but you can also make use of this charge transfer steps at interfaces to do catalysis. Okay, so this is a big leap. This idea that charge generation in organic materials is possible through making donor-acceptor interfaces is the fundamental concept of how to generate free charges. Okay, I just wanted to sort of put this in context because I think the slide share has a problem. There is this last line that you can see in organic molecules and in the physics parlance, trapped charges or charges which are formed in organic backbone are never called as free charges, simply because every time an electron resides on a molecule, the electron is not in a conduction band. It actually strongly interacts with the nuclei of the molecule. And that interaction allows for any kind of structural change, because if the electron from a neutral molecule, a molecule is reduced to become a radical anion, the structure of the molecule automatically changes, and that is essentially called the trapping of a charge on a molecular backbone. And in physics terms, it's called a polaron. So excitons are pair of charges. Polarons are individual charges trapped in the molecular lattice. Okay, so these definitions are important to clarify because we will move forward and use some of these nomenclature again and again in our explanation. So let's see how typically people use these polymers and make a solar cell. What you do is a simple technique. Alan Heeger, who is a Nobel laureate, who won the Nobel Prize in 2000 for developing conjugated polymers, he actually came up in 1991 a design that said that, you know, as simple as a polymer mixed with fullerene in a solvent mixture and made and spin coated on an electrode should be able to generate some solar cell efficiency. Okay, this was the time when dye-sensitized solar cells are also getting discovered by Michael Gretzel. 1990s was the time of real discoveries in this field. Okay, the pioneering discoveries, and mixing a polymer with a fullerene created magic. Okay, the magic is this way. You can see that these solar cells are called bulk heterojunction solar cells, simply because what you just do, you take a solvent in which polymer donors and fullerene acceptors are mixed together, and you spray coat on an electrode. Okay, and what you see is you see these interpenetrating domains, so called as heterojunctions, form. And these heterojunctions have finite widths. I have shown this here in a zoomed out image where the green ones are the polymer network and the red ones are fullerene balls. Okay, they have been phase separated but at the nanometer length scale. But these are interpenetrating domains. Okay, so now you can clearly see that if I were to excite this kind of system, that means a solar cell is made out of this and light falls on it, you can create excitations in the polymer network, and these excitations can migrate to the interface or the junctions where the polymer is looking directly at the fullerene, which is its redox partner. And when the excitation comes close to that interface, electron transfer happens or charge transfer happens, and you create weakly bound excitons. These are called charge transfer excitons. As I said, these are absolutely 1/10 the energy, binding energy, than the typical silicon exciton binding energy. So once that is done, you can actually move out these charges across with the separate junctions and connect it to the electrodes, and you create a solar cell. This was the simple concept initially given by Alan Heeger and then later developed by Richard Friend in a beautiful paper in Nature in 1995, where he showed 6% efficiency solar cell from Cambridge. Okay, so Alan Heeger is in University of California, San Diego, and Richard Friend is from University of Cambridge in UK. Okay, these two pioneers have changed the way we think about organic solar cells. So a simple spin casting, you don't even have to think about it. Simple spin casting on an electrode makes this simple solar cell design work. And the key to this is the heterojunction architecture, the nano architecture, which creates this multiple CT interfaces, many CT interfaces. If I were to However, make this device with a coating, a layer of polymer, and again a vapor deposited layer of Fullerene acceptor, the number of interfaces that we could have found would be limited. But since we have admixed them, we have mixed them together in a solvent, we have let them really mix well, and when they are dried and put on a film, these heterojunctions form, and there are multiple such charge transfer interfaces. With this idea, what are the current trends? Almost 2 years back, there have been reports in Science which have shown that organic photovoltaics have reached an efficiency of 18%. Okay, and some of them have used not Fullerene but non-Fullerene acceptors. But I just wanted to mention that in India, in the lab scale, my colleague Professor Dinesh Kabra from IIT Bombay, very close by in the campus, he typically makes these organic photovoltaics in the lab. Now it's not 9% anymore. He can go up to 12%, 11 to 12% in his lab scale devices with Fullerenes. And of course, there are other places in the world that are doing non-Fullerene acceptors, and you can get to sort of these numbers of 14 to 15%. These are slightly older numbers I've shown, but what I really wanted to show here is, for all the ideas of solar cell efficiency, the solar, when I buy a battery from a store, what I look at is the voltage it gives, right? So when I think about voltage from a battery, these solar cells, their efficiency numbers mean something. But what we should really be bothered about is what is the output voltage of these batteries. So if you were to look at these numbers, even with really nice numbers, the potential you extract out of a solar cell is close to a volt, okay? Actually less than a volt in some cases. And most of the time, they make use of materials which absorb in the visible, okay? And visible energies are close to 2 to 3 electron volts. So we are deriving a volt of potential by giving in photons which have energy of 2 to 3 electron volts. That means we are not doing a good job of actually extracting out voltage from these devices. So it's important to understand what really goes on phenomenologically in a solar cell from the perspective of energy balance. Okay, so this particular image shows that when I create these excitons in a system, I create charge transfer states because at interface there is a charge transfer. And then I create charge separated states when at the interface the electrons and holes move opposite directions. They create this charge separated states. And once these charge separated states reach, or the charge carriers reach the electrode, they can get injected and you can generate output, a voltage output. However, you can clearly see the energy that is put in is lost incrementally through these states, and at the end you only get half the energy that you can extract out. The electrons have half the potential, okay, at least half the potential. This is just a cartoon design for some of these solar cells. When you look at what defines efficiency of a solar cell, eta, it actually is the output potential, which we call as the V, but it's defined V into I essentially. But when we sort of define it, we define it by a sort of a theoretical best of the device, which is the open circuit voltage. Now this VOC is critically dependent on where the electrons, at what energy level the electrons are getting injected, how much energy does the electron have after going through all these states to be injected in the electrode. So that's where the VOC is set. How many electrons are injected is the JSC, or the current, the short circuit idealized current from a device. And the fill factor is essentially accounts for all non-ideality of the solar cell device. So that means 100% of a fill factor will be an ideal device. However, in typical devices, these fill factors are on the order of 70 to 60%, 60 to 70%, which tells you that there are losses in device making as well. These are not clearly perfect IV devices, okay? And the input power is nothing but the solar power that falls on the solar cell, and that has been calibrated to one sun, and that is 100 milliwatts per centimeter square, and you can estimate for any solar cell device what is the efficiency. Okay, now it is clear that the efficiency is being compromised because there is losses of energy as the electrons or the states are being traversed by the system. Okay, so as you traverse different states, the excitations traverse different states, you are losing energy, and at the end the electrons get injected at much lower energy. So there is a critical need to understand how do we lose these energy, and how can we mitigate this problem. So our lab critically has looked into this problem, and that's what we will discuss, what we call as energy relaxation dynamics in these systems. What that means is, with all excitons, you can sort of have relaxation, loss of energy to the CT states, because CT states are lower in energy. So if it's possible, can you traverse it without loss from a CT to a CS and inject somewhere here? For example, let me make the pen, draw the pen out. You can go from here, stay here fast enough that you can drop down to this level and then inject, okay, rather than thermalize and relax and then inject. So these thermalization leads to losses in energy in the states. So can we beat thermalization? Can we do things faster than thermalization so that we can inject electron with higher energy or potential? The other aspects in the group we look at is different kinds of mechanisms of light trapping. Okay, so let's quickly go through what people have already thought about in this problem. People have actually looked at these relaxation problems through morphology dependent making of devices, a morphology control on devices, and solvent plays a critical role in this, because when you make films out of these materials, a combination of donor acceptor materials, solvent has to evaporate. Okay, this green, this blue, dark blue circles I've shown are residual solvent molecules. So solvent engineering plays a critical role in defining interfaces. So it's important to understand this as well. And we have worked previously on this with one of my graduate students, Palash, where we showed that there is a memory of in the morphology of what existed in solution before we made the film. So as you remember, we put these two materials together in a solution and dry it out. Okay, so when we put it, it equilibrates, and there is a morphology in solution, and the memory of that morphology in solution gets translated in the film, and that's what we showed in this paper. But that's not all, right? So we have to really understand, when we make a film, we really have to understand how these excitations travel, how these excitations generate charges, and where are the losses, the critical losses. Okay, so the problem to a physical chemist boils down to this diagram. This diagram is nothing but an energetic accounting, a thermodynamic picture, where we think about when we start from a neutral polymer mixture of donor and acceptor, when we excite the system, what are the possible states that it can access? When there is a charge transfer, what are the possible states it can access? When there are generation of charges, what are the possible states that it can access? Now, to understand in a simplistic picture, we started by looking at covalently bound donor acceptor pairs, not non-covalently, not the kind of Fullerene polymer pairs, which we will discuss later. But we started with understanding, even at the basic level, donor pi acceptor systems. Okay, now this is the pi bridge, which I talked about at the very first slide. And these are charge transfer systems which are covalently coupled to each other. These are polymers again. These are used for solar cell applications, but they become critical as fundamental understanding point of how charge transfer can be controlled at the molecular level. Okay, so we looked at the exciton dynamics in these systems and looked at how excitons can be converted to charges at this interface, at the donor pi acceptor interface. Before I move into this idea of watching these excitons in these molecular framework, I would like to give a brief account of what excitons typically do in a molecular backbone. Excitons have this propensity of spreading out. These are excitations in a conjugated backbone. So you can have multiple conjugated monomers or monomers getting excited. So these excitons actually have a large delocalization length initially. Then they actually can localize into few of the chromophoric units. And then due to nuclear backbone changes, they can actually relax, lose energy. And then because once they are relaxed, they can actually hop between chains from one part to another. Okay, so all of these processes are very fast time scale processes. I have mentioned in femtoseconds, FS, it's femtoseconds, 10 to the power minus 15th of a second. So 30 femtoseconds, 200 femtoseconds, 1 picosecond, 10 picos. These are very, very fast processes indeed. And to watch these excitons lose energy, get transferred, hop in the backbone, you really need to develop tools to follow these in the dynamics, the dynamical picture. Okay, so what we typically like to do is, once we know what is the spectral signature of an exciton, something that I think spectroscopy is something that even in the previous talk Dr. Rachna mentioned about PAT, where she said that process technologies require understanding of materials, use of techniques, analytical techniques to understand materials, like doing IR, Raman, UV. All of these are spectral analysis of molecular systems. And this is exactly what we do. We want to look at the spectral signatures of an exciton, of a charge, and we do not just want that. We want to watch this over time with this kind of precise time scale. So how does one think about this? This is the entire field of time resolved spectroscopy. What do we do in time resolved spectroscopy? Well, just like what you do when you capture an event with your camera, with your cell phone, you make a movie out of things, right? We would like to make a movie of exciton migration and diffusion. It's exactly like capturing frames, right? Something that was developed for the first time by Edward Muybridge, who was this famous cameraman who placed a bet with Leland Stanford, the original billionaire who funded Stanford University, as we know it. He placed a bet, and Leland Stanford would go to race courses and place bets, of course. But he placed a bet that with Edward Muybridge, that when a galloping horse runs the course in the race, he said only every time two of the legs will be on the ground. But Edward Muybridge said, no, a galloping horse should have all four legs at some point of time in air. To capture that event, Edward Muybridge did develop a millisecond flash camera work, which you could realize, and you can clearly see these are the first flashing camera images, moving images of a galloping horse. Okay, and it is clearly seen in one of these images, all the four legs are in air, which ensured that Muybridge wins the bet and develops time resolved spectroscopy as in its nascent beginning. Okay, so Now here is the part. How do we implement it? How do we implement a camera in the lab? How do we implement these kinds of time scales? 10 femtoseconds, 30 femtoseconds, 1 picosecond. That's really fast, right? So this absorption time scale, of course, is few femtoseconds. We all know that. So there is a way to do these transient events by a method called pump probe spectroscopy, which is nothing but that you go up. When you excite a system, you go to its excited state. These are potentials that I have shown. These are nuclear potentials that define the ground state. These are nuclear potentials that define excited states. And when you excite the system, you basically launch the system in excited states. And for each point on the excited state, if you can get spectral signatures of point 1, point 2, of the third point, fourth point, fifth point, you should see the sort of you should get information of the excited states in form of changes in the nuclear the nuclear architecture of the molecule. The structure should change, and for all of these points, an absorption event which happens in few femtoseconds will be followed by another absorption event which happens in few femtoseconds to do a time resolved transient absorption. At each point 1, there will be an absorption event. There will be a spectral signature that you will collect. At point 2, you will again collect an absorption spectral signature. Point 3, and so on. You would like to do this and collate a movie of how this entire state evolved from 1 to 6, a new state that has formed. Okay, so these are essentially the idea of excited state evolution, where we follow electronic states. We can follow absorption, we can follow vibrations. So this cute little cartoon that I have for all of you is something that we think about all the time in the lab. It can be evaluated in terms of a race. When we start a race, it's like a 100-meter dash. You have a gun, you start the race, and everybody starts running after hearing the sound of the gun. And then you come and probe how much the molecules have reacted at different points of time. You have a stopwatch, you click the stopwatch at various points and you watch where the molecules are. And you collect spectral information, something like this. You get data at 1 picosecond, 15 picosecond, 500 picosecond. Every time you get UV spectrum, you get absorption spectrum, you get information of the color of the molecule at each point of time. And these temporal maps are giving you a movie, a motion picture of the entire event. Okay, so exactly this way excitons can be followed. But sometimes excitons become hard to follow with just absorption, because absorption signatures could be broad, and not just excitons are generated, charges are being generated. So that in itself becomes hard to track in transient absorption, because you have overlapping signatures. Here, for example, this broad signature is an exciton absorption, but on top of these small shoulders are essentially coming from radical cations and radical anions, means charges, means polarons. So you have to carefully subtract and get this spectra, and it becomes hard to do. So here is where our collaboration becomes important to discuss with Professor Satish Patil in ISC Bangalore, where we got these polymers, and you can see that these polymers have a visible absorption, and they can have excitations generated in the system after you generate excitons. And these excitons, which are peaked at 1000 nanometers, you can clearly see they are changing, they're going down in time, they're decaying in time. But there are features at 1400 nanometers which kind of sort of remain, and it becomes important to sort of describe these systems, what the complicated natures of these spectral signatures are. And just transient absorption does not help in completely understanding these spectral signatures, because you can clearly see these signatures have sort of different meaning when we excite at different parts of the absorption spectrum of this polymer. In fact, if you do a wavelength dependent excitation, the excitonic part goes down, and the charges, the trapped charges part, actually become very, very significant to significant in our transient absorption spectrum. This kind of analysis is important. However, it does not clearly tell you what is the sort of a molecular nature of the backbone when excitons are decaying or when charges are forming. So for that, we do vibrational spectroscopy, something that is so close to our heart, because Raman spectroscopy was developed in India, and we do Raman spectroscopy in the lab, time resolved Raman spectroscopy. And the idea of this technique is to capture vibrational resonances in the molecule. What it means is, in any molecule, when we look at the ground state, there are vibrational states that are within that electronic state. And these vibrational states, they have specific energy gaps. And if you have to measure this energy gap, typically you would do a IR measurement. These that will report you as the vibrational frequencies of your bond stretches, the bond bends. But in Raman, what you do measure these gaps, but you go through the excited state if you are doing resonance Raman and come back to the ground state. So the energy absorbed by the system, it's an inelastic process. You give a large amount of energy, the photon gives energy to the molecule. The molecule again dissipates the energy as a scattered photon, but it keeps some bit of that energy to excite vibrationally itself. Okay, it excites itself vibrationally, and you can measure that much of energy, because the separation of the excited photon energy and the scattered photon energy is this vibrational gap. Okay, and that's what Raman spectrum scores for you. So you can actually do Raman spectroscopy at the time resolution of few femtoseconds, and this is a method that we follow in the lab. Maybe at a later point I can have a separate tutorial as to what this technique entails, but just take it for face value for today's talk that we can measure transient Raman snapshots with few 50 to 100 femtosecond time resolution to capture again moving images of excitations in system. This is an example of polythiophene film. You can actually do Raman spectra of the ground state of the film and the excited state when the trapped charges are formed, these polarons. And you can clearly see that the polaron spectrum at 500 femtoseconds, really fast, is completely different than the neutral state in the ground state. There is this 15 wave number red shifted in the C double bond C stretch feature. This is the vibrational mode. Okay. We have built this system, and the students in the lab have worked hard to put these systems together. I'm going to just skip these steps and come to the major part of the research that I really would like to highlight. This particular example where you have a donor pi acceptor framework of a polymer. Okay. So these materials are being used to make solar cells. The device efficiencies of these solar cells containing these kinds of polymers are close to 5 to 6%. They're not pretty great. And one of the things is the loss in energy that we have in these systems. And when we do transient absorption, where we actually get these moving snapshots of excitons, as I said, we can quantify essentially the time scales of these evolution of states. We can clearly see that there are two features that are present in the spectrum. Both the features decay, but you have slightly different decay rates for these features. Also, at different wavelength excitations, these features have different contributions to the transient absorption, which tells you that these polymers have different subpopulations. When they are in a film or in solution, there are different subpopulations that give different kinds of excited states. So this is, a chemist completely misses out this point, that the chemist thinks that whatever in solution, the properties of the polymer in solution exist, The same will be the property in film, but that's not true. In a film, you might have different kinds of populations of polymers stacking together, polymers making interfaces, and these populations can have completely different exciton lifetimes, completely different excitonic properties, completely different charge propensities, charge trapping propensities. So it's important to understand these spectral features and look at their population changes upon excitation and see if there are features that live for long. And we indeed see a long-lived exciton in these systems, and we assigned these systems by very carefully looking at their emission properties, as well as we assigned the other features, spectral features of the transient absorption as charges by sort of changing concentration and letting these polymers aggregate and allow for inter-chain electron transfer to be larger in propensity in aggregates as compared to in monomers. So when we change these concentrations and look at the transient absorption features, we could clearly see that the feature at 1400 is clearly concentration dependent. Okay, so that tells you that it has a charge transfer character to it. And this is the model that we have, that these polymers aggregate. They can aggregate on themselves. They can create charge transfer interfaces within them, but they can also have charge transfer within one strand. And that's essentially the nature of the exciton, that within the same strand, you can have a charge transfer. That basic charge transfer at one monomer unit, donor pi acceptor unit. Okay, so can we selectively probe the exciton? And that's what we did with transient Raman spectroscopy. And of course, with Raman spectroscopy, you know that we have to understand this in terms of the vibrational modes in the system. So I'm just showing few aspects of regular normal modes in vibrations in these polymers. They are very complicated, but you can clearly see, you can identify certain normal modes like the 1367 mode and the 1509 mode can be identified as part of the acceptor framework of the donor pi acceptor system. And you can actually identify certain normal modes which are from the donor part, which are at 1320 wave numbers, which we again collected using our Raman spectrometer. You can also see that you have the vibrations of the bridge, which are different. And this is really the critical part of the talk, where you can see CH in plane motions of the vibrations of and the thiophene stretches. Thiophene stretches are at 1422 wave numbers, and the thiophene bends, the CH bends in thiophene are at 1228. So we can actually color code these vibrations based on the chromophores that we have in the conjugated polymer. And when we look at these snapshots in time, we know that we're going to only watch the exciton because we ensure that we are in resonance with the exciton. We ensure that the Raman excitation is in resonance with the exciton. We can watch the vibrational modes evolve in time and collect Raman snapshots. You can clearly see 0.3 picoseconds, 0.7 picoseconds, 10 picoseconds. The vibrational spectra has changed. The intensities have changed of the 1228 and the 1422. You can clearly see the intensities are changing. And these are coming from the thiophene part of the chromophore, the bridge part of the chromophore. And there are, of course, changes in the donor and the acceptor part. The acceptor and the donor part of the molecule. And we did very detailed analysis to come to terms that there is an important event that happens in 400 femtoseconds. And that event is clearly captured. The intensity of this 1422 peak rises with the 400 femtosecond time scale. And that rise in the intensity in both the intensities of the bridge clearly indicates that the bridge actually has a larger Raman cross section once it starts moving and it starts coupling the donor and the acceptor units together. and it forms a planar state. So typically in these conjugated polymers, these bridges are non-coplanar with the donor and the acceptor. When it is excited, it goes up that way and the non-coplanar. But then in the excited state, the bridges planarize and they couple the donor and acceptor. And that is the time scale of 400 femtoseconds, which actually leads to a charge transfer state being generated. And that we identified as the formation of intramolecular charge transfer state, which is still not equilibrated. It's 400 femtoseconds, still not equilibrated. It's hot, as we call it. And then it takes time to localize and relax. And this time scale is mode dependent, and it takes 1 to 10 picoseconds to localize into the original donor and acceptor units. That means the charge is localized. That means the acceptor becomes radical anion, the donor becomes radical cation. And these localization time scales are 1 to 10 picoseconds, which we also followed and tracked by Raman signatures. Again, telling us that the critical motion is the thiophene bridge motion, and everything else is just cooling and localization on the donor and acceptor units. So this told us that if I have to think about energy relaxation processes, if I have to ensure that I can take out the electron at a higher energy, I would like to avoid the localization and the ICT afterwards. Okay, so within 400 femtoseconds, if I can generate, I've already generated a CT state in the backbone, but if I could push the electron out from this particular state, if I can push the electron out, I will actually sort of gain, I can keep my energy of the electron right up there without losses in thermalization and push it out. So this is something that we think is the reaction coordinate for generation of charge transfer states in a donor pi bridge acceptor system, which that means the time scale of that motion critically dictates the time scale of charge transfer. So if you could position your acceptor close by and within 400 femtoseconds the electron can jump out, you can preserve the energetics. Okay, and that's what sort of we did. Something that there was a paper previous to us that also showed that thiophene bridges are important, but we actually watched this using Raman instead of electronic spectroscopy, which was done by Scholes at Princeton, who did a lot of 2D electronic spectroscopy to watch this. And electronic spectroscopy has large line shapes as broad line shapes. So it was clear that we could sort of enumerate this sort of idea that the backbone structural changes are the key to controlling the charge transfer processes in excited polymeric systems. We actually went on to sort of look into other kinds of polymers where we could enumerate the role of polymer packing and morphology. That is also important. Not just the backbone, but the side chain of the polymer is also important for these excitons and charges to be generated in requisite time scales. We again collected Raman snapshots of generation of trapped charges with right morphology of a side chain. And we could see again a couple of picoseconds that are important for these charge generation steps within these organic polymers. Okay, and all of these again, these charges, they can sort of cool within few picoseconds. Okay, so within 5 picoseconds, the polarons cool down or the charges cool down in these kinds of systems. That's what we are learning. So if you were to have electrode interfaces where you can extract charges within 5 picoseconds, that would be necessary to make a very, very good solar cell. And so there are, of course, not just these individual polymers can be looked at in films, but you can make blends of donor acceptor blends like I talked about in bulk heterojunctions. You can look at those, and these are some unpublished data, recent data from our lab, which we are trying to put together. We have now enumerated that these charge transfer charge transfer states at the interface could be different from the trapped charges generated inside the polymer using Raman spectroscopy. Again, I won't have much time to talk about this right now, but I just wanted to say that even in neat polymer, you can generate polarons and charges, but these charges are slightly different than when you have the interface with a acceptor, a Fullerene acceptor. You can start seeing the shoulder features which are coming from the Fullerene anion radicals, and a slightly different C double bond C stretching feature of the polaron when they are at the interface as compared to trapped, deeply trapped in the polymer network. So these are bulk trapped charges. These are interfacial charges that we have enumerated from the transient Raman measurements. And this is something that we are very much excited about, that Raman can help us really understand the nature of the states at the interface from the perspective of the molecule. Okay, how the molecule sees the charges, and that's because we are looking at the molecular vibrations, and molecules are reporting through the vibrations how it sees the charges, right? So we actually now have a 1435 wave number feature for P3HT polaron, which is distinct from the 1425 polaron feature, which is purely for the bulk polymer, and PCBM feature, which is the Fullerene feature at 1460 wave number, which is distinct from what was published previously in a science paper 6 years back. Okay, so I think these are some of the things that we are concerned about from a fundamental aspect when we make blends and we look at the energy relaxation and signatures of the states that form and what are the energetics of these states. So as a summary, it is important to sort of emphasize that the first few picoseconds after excitation in organic polymers is critical. Your chemistry has to be such that in the first few picoseconds, you already do charge transfer and electron transfer from the polymer backbone, and you can sort of extract the charges out from the monomer part. Okay, and that is the challenge. That is the challenge: how to develop such thin solar cells, how to develop cells which can have these materials really closely packed to the electrodes. There are other aspects to this work in our lab. We, of course, look at energy relaxation and try to understand that, but we also look at new mechanisms of light harvesting. And as I said in the initial part, we also look at a process called singlet fission, which is multiple exciton generation in solar cells. And this is a method by which, this is an absolutely contemporary method by which you can boost up solar cell efficiencies by generating two excitations by one photon. And Mark Baldo and group have shown in 2019 that you can make solar cells of silicon and enhance its efficiency from 29 to 35% by making a singlet fission layer, which is an additional layer that could trap additional light in the UV to visible region and essentially give more charge carriers to the original silicon solar cell and boost up its efficiency. So we are also looking into these materials which can do singlet fission. One of my really talented senior student, Arup Kundu, has been looking at materials like carotenoids, which are natural chromophores found in plants. And he has recently shown that these carotenoids can be packed properly as in nanoparticles, and then these nanoparticles have long-lived triplet excited states. And using transient absorption spectroscopy, as you can see, we can actually separate out these intermediates, these initials. So the idea is that you excite one chromophore, the other chromophore remains unexcited. So you generate one exciton in that chromophore, and the other unexcited chromophore just is sticking around. But then by a process called singlet fission, they share energy, and both the chromophores become excited at half the energy cost. And they form something called as a triplet-triplet correlated pair, which is a singlet. And once that triplet-triplet correlated pair dissociates, you can form two triplet excitons. And that's the idea of singlet fission. And that's what Arup showed, that you can do this in carotenoid framework when you make carotenoid nanoparticles and pack these carotenoids in nanoparticles. You can create these triplet correlated pair, and you can watch the evolution to free triplets. This is something that is we have submitted for publication. So these are some of the very interesting ideas that the contemporary literature, the recent advances in the contemporary literature of photovoltaics have dealt with. We are being a humble part of this process. We are trying to do as best as we can, as we understand the mechanisms, and use transient tools, transient spectroscopic tools to watch these excitons in action. With that, I would like to thank my entire group, evolving from 2018 to 2020, where you can see the major players here. Polash, who was sort of part of this major work, and then Arup, of course, who is now doing the work on singlet fission, and other students who have been Abhinandan, and other students, Gokul, who is not here in this image, but who have been part of this entire process of looking at excitons. And this is the recent picture from the group, same in the TIFR garden, having a moment, a nice moment in sun. And I would like to thank Professor Ravi Kishore and Professor Kiran for kindly inviting me for this meeting. And I would also like to thank all my collaborators whom we are collaborating with, especially Professor Satish Patil from ISC Bangalore, who supplies us with these very nice conjugated polymers to look at, and Professor Anil Kumar in IIT Bombay, who actually gave us very good regio-regular P3HD. Okay, and thank you all for patiently listening. I overshot, but thank you very much.
Thank you, sir, for that very informative talk. I have a set of few questions here for you.
Yeah. Thank you, Dr. Kiran. Yeah.
Yeah. What is the lifetime of these photo carriers in presence of dopants or defects in case of polymer conjugated organic frameworks?
Very good question. So the lifetimes shorten. Typically, you can have shortening of lifetime. So, for example, if I were to just have a pure material in solution, the lifetime of conjugated polymers are typically hundreds of picosecond to a nanosecond, at best to a nanosecond. When we make a film out of this pure material, these lifetimes go down to 50 to 100 picoseconds. When we have defects or dopants, these can actually be shorter. Okay. However, in certain cases, you can also have recombination events that can create radiative processes. So they really depend on the context, and I think these polymers are very sensitive to the environment and the morphology they are in. And if it is packed very well as crystalline aggregates with right donor acceptor morphology, then the lifetimes will be as short as few picoseconds, because you will have charge transfer and other charges being generated.
Yet another question. In TDPP BBT, what will be the difference in exciton generation and charge transport process without the thiophene pi bridge? And what will be a good replacement for the same, and why?
Okay, so could you just repeat the question one more time?
In TDPP BBT,
yeah.
What will be the difference in exciton generation and charge transport process without the thiophene pi bridge? What will be a good replacement for the same?
That's a great question. Okay, so if you were to just so I'll stop sharing. Okay, is that okay? Yeah. Okay. Yeah. So if you were to generate the excitons without the thiophene, the problem is that these molecules will always be orthogonal to each. The chromophores will be orthogonal to each other. This is because all of these have side chains associated with it. And when they are orthogonal, they would never be able to couple for a charge transfer in the backbone. Okay. So they need to couple to generate a charge transfer delocalized state. So if you do not have them, they will just emit. They will not have this charge transfer component. The local donor and acceptor can individually work. The excitations could lead to just emission. And replacement, well, you can have multiple thiophenes intervening the two donor and acceptor systems, and or you could sort of think of ways to clearly make the thiophene rigid. Okay, so here is one example. I just have to share the slide one more time. Sorry about that. If I go to the slide share option, present now, a window, this one, share again. Okay, so if you were to, I kept one slide there for this part, where you can clearly see that if I were to make the thiophene bridge non-covalently linked to the acceptor part, you could probably planarize the thiophene and keep it for a large charge transfer coupling.
Thank you, sir.
And there are a couple of questions from the YouTube, right?
Yeah, but due to want of time, I will take just one more, and
Sure.
then we'll
Sure,
send you
sure.
the remaining
We'll-
questions by mail, maybe.
Absolutely.
One last question, sir. Can we have
Yes.
both the acceptor and donor moieties in a single molecule? Uh, I think you have answered this, but the main question is, how will the efficiency be compared to the same being in two separate moieties?
Great question. Yes, when we couple the donor and acceptor in the same molecule, there is a good part. The good part is the charge transfer coupling increases. That means you will definitely do charge transfer. There's no question about it. However, the separation part becomes a problem because you have to take out now the charges from that backbone and dump it off to another backbone or another molecule, right? So you can actually make use of TDPP, for example. TDPP is a donor conjugated to an acceptor. Donor, acceptor, conjugated by the thiophene. But again, this problem is once you generate the CT state, you need to take off the charge. So how do you do that? So in any case, you will have to have an interface which is non-covalent in interaction or nature. So you will have to have donor material and acceptor material interacting weakly, because you just need to migrate the charge from one to another. But then once that migration takes place, you should have a channel or a pathway through those individual materials that the hole and the electrons can be transported. So the conductivity of hole and electron in these materials are critical for us to understand. That means not only these polymers become great sources of charge transfer, but they should also become great highways for movement of electrons and holes. So that's how we think about this problem. It's not just the donor and acceptor, because the donor and acceptor is really my framework to create charge transfer. But it has to be thought of as a material that can do hole conduction or electron conduction. So it really has to do with the individual particle conductivities. And that part is not associated with redox potential. That part is associated with within the backbone, how the states are arranged for electron hopping or hole hopping. And so to answer the question, you require two different materials simply because you want electrons and holes to be separated.
Thank you, sir, for that.
And the efficiencies sort of go up when you have separate materials as compared to when you have just the like covalently coupled materials.
Thank you, sir, for that beautiful presentation and such a simple explanation of the concept of excitons and the use of pi-organic materials, pi-conjugated organic materials for generating the same. And also the way you explained to us how to observe these excitations using various techniques. I'm sure the students have really relished this talk. We look forward to many more such interactions with you in the future on various such topics.
Sure.
Thank you, sir. Thank you once again.
Thank you very much. Thank you very much for this opportunity, and thank you to Dr. Kiran and Dr. Kishore. Thank you.